morning, good evening, good afternoon. Now let us start a series of lectures on mineralogy. This is chapter 3 in Open Geology textbook. At that same website, opengeology.org, there's even a full mineralogy textbook if you wanted to dive deeper than what we're covering here at the introductory level. As we get started, I do want you to recall some basic aspects of chemistry. Elements, atoms, and bonding. Because it's these chemical, features is the right word, behaviors maybe, that are actually going to control so many aspects of mineralogy. And we're not going to get into those things, but it's going to control properties like color and mass and hardness and symmetry. All these aspects that matter so much for mineralogy are really just chemical things that we're then directly applying to the world of earth science and minerals. Where we get started with mineralogy is a definition. In fact, this lecture is going to be really kind of note heavy, not very many pictures. And I think what we can do is we can structure our notes for this lecture off of this definition of around 20 different words. And so what we're going to define a mineral as is it's a naturally occurring crystalline solid. And I'm going to have to naturally occurring crystalline solid with a definite chemical and homogeneous composition, usually formed by inorganic processes. So let's get that down, and then we're going to unpack it. So naturally occurring crystalline solid with a homogeneous, definite chemical composition, usually formed by inorganic processes. Usually formed by inorganic processes. For my students, I want you to memorize this definition and be able to regurgitate it. And then what we're going to do now is just make sure you understand it, because naturally occurring crystalline solid, definite chemical homogeneous chemical composition, usually formed by inorganic processes, all have significance and meaning that I want to unpack now for the rest of this lecture. So let's do that. Naturally occurring is the simplest of each of the aspects of what defines a mineral, and this means it occurs in nature and that it is not man-made. Right now, there's a huge economic significance of synthetic diamonds. They are a mineral in every aspect of this definition. They are real even, but they are synthetics because they are made by man. So they are not synthetic. We could put that down here. There's value to them, no doubt, but they don't satisfy this definition. Number 2, crystalline solid. Now this one, solid. This one's an interesting one. This means it has both internal and external symmetry. And it's the external symmetry is the outward manifestation of the internal. So I think internal probably is even more important. Well, it is more important for sure, because all minerals have internal symmetry. Not all of them will have external, as you'll see soon. So for internal symmetry, what I mean is that the atoms are arranged in a lattice at the atomic level, and the bonding goes between those individual atoms. And there's a structure here, like Lego blocks, that is repeatable infinitely in these different directions, but it's at the atomic scale. And I'll even put that word lattice. The lattice itself has symmetry to it. We probably don't need to go too much over the top here, but we could do like a mirror. This dot right here is symmetrical with this dot right here about a reflection on this mirror plane. All right, this is the kind of thing I want you to be thinking about as happening at the atomic level with respect to internal symmetry. Now, external symmetry is similar, but it's what we actually see in hand sample. And these external bits of symmetry are defined by reflections and rotations. All right, so I just showed a reflection over here. We could do the similar. We could say, all right, so here is a shape. It is a rectangle. Now, where are the symmetry elements in this with respect to a reflection? Well, we could draw a mirror plane right here, and the left and the right are the same. We could draw a mirror plane in this direction. Left or up and down are mirror-like reflections about one another. Now, rotation means you can spin it and see the same shape. So we could do, let's see, here's a square. This, we would say, has a fourfold axis of rotation. Here in the middle, A4 is just our shorthand for it. If we spin 90 degrees, this box looks identical because it has a fourfold symmetry. Let me draw another one here for you. It's a hexagon. Okay, it's a sloppy hexagon, but it'll look the same with a 60-degree rotation, and this would be a sixfold axis of rotation. Okay, and so all minerals have to be naturally occurring, and they have to be crystalline solids. Now, what's next up here? Homogeneous, definite chemical composition. All right, so let's get this down. 3 is homogeneous. That means same throughout. And definite chemical composition. That's a bit of a mouthful. And all this is saying is that there's a chemical formula. And if the mineral deviates from that chemical formula, it's a different mineral. The example might be NaCl. This is table salt. It is always NaCl and is NaCl throughout it, homogeneously and definitely NaCl. So if we had potassium chlorine, that's actually a whole different mineral, and its name is sylvite, whereas this one is halite. Halite tastes good, sylvite tastes real bad. All right, I mean, what other things we could do? Diamond is carbon, and quartz is SiO2. Great, okay. Now, usually inorganic. This one has gotten a lot of pushback in recent decades because it used to be like always inorganic, but then the people who studied shells and fossils and corals and planktons, they started to say, hey, hold on a second. These are minerals, but they're biomineralized. And so what we're going to just say nowadays is we're going to say things are usually inorganic, but we're going to say biomineralization is okay. Biomineralization is okay. And we could have a shell. Here's like a snail shell. And you can imagine that as that organism is growing, it is soaking up calcium from its environment, and it's actually making a real mineral. The organism is secreting a mineral. All right, so there's our definition for what is a mineral. Now, to finish off this lecture, I just want to go through the ways or the locations where minerals can form. So mineral formation, and really we're going to go into mineral formation. And what we're going to do is we're going to get into the 5 environments for mineral formation. But before we do that, I just want to emphasize one thing, is that mineral formation requires 2 steps. It requires nucleation and it requires growth. Whereas nucleation, that is the seed, the nuclei, the embryo is being stabilized by thermodynamics. It's like Gibbs free energy is lowering, and this one little seed becomes a stable crystal, probably at the nanometer scale. And then growth is the delivery, the addition of new material as ions become available, okay? So, okay, that makes sense though. Growth is the addition of ions as they're attaching to that crystal structure, and this is the formation of a stable embryo. There's gonna be 5 environments that I would like you to understand. Mineral form then. All right, so our 5 environments for mineral formation include precipitation from a liquid. This is ice on the surface of a lake, although probably in this class I'd rather have you think of like a magma chamber deep in the subsurface, and in that magma chamber, which is liquid, there are crystals growing inside of it as ions like aluminum or silicon attach onto those minerals. Number 2, we're not getting into these things very deep, okay? These are just the environments where they can occur. We also can have minerals grow from precipitation from a gas. The best example here is also from a volcano, but a fumarole. What is a fumarole? A fumarole is like a hot spring. It's a gas crack where gas is seeping out the side of a volcano. And the temperature of that gas goes from 400 Celsius to 30 Celsius over just a few meters. When that happens, as you cool down, you can actually freeze out and make a crystal. And so the best example here would be sulfur at a volcano. Precipitation of a liquid, you could just say like crystallization of a magma chamber. Number 3 in this list is solid state change. This is a kind of a weird one. I want you to associate this with 2 words: diffusion, and I also want you to associate it with metamorphism. Minerals can become unstable as temperatures and pressures rise, or they can become stable as temperatures and pressures rise. And the best example of this is, like, think about the Himalaya. The Himalaya is this mountain range where 2 plates are colliding into one another, right? India is colliding into Asia. And down in the depths of this mountain range, the rocks are so hot, they're flowing and they're folding. And the minerals here can actually start to change and grow. This is the metamorphic environment at high temperatures and high pressures. In the sedimentary lecture, we talked about shale. This is a mudstone. But if you metamorphose a shale, you can create something called like how about this? A garnet schist. They look totally different. A garnet schist might have these big old chunky beautiful garnets inside of it, and the rock could be all folded. And it started off as just this boring black shale. That is creation of new minerals by solid state change, where everything is happening very slowly as ions are diffusing in this very hot environment. Number 4, we sort of already talked about. This is biomineralization. Biomineralization is where the organism will extract ion usually from seawater for body part or shell. I suppose you could say, although shell is somewhat restrictive. Calcite, for example, can be made from coral, and that produces the limestone, the calcite limestone rock that we've talked about so far. We could have silicon, actually I'm going to say silica and plankton, right? And this is actually making chert, which is a rock made of quartz. That's the examples of biomineralization. And then the last part of the lecture here today is the number 5 is change by weathering. Do you remember the different weathering reactions I taught a few lectures ago? There was hydrolysis, and there was also oxidation. So these 2 reactions basically make one mineral unstable and convert it into a new mineral. Oxidation, that would be something like iron goes to rust, and minerals with iron will go to minerals that are rusted, something like gutite or hematite, as oxygens are added to the iron. Hydrolysis is the formation of clays, and clays are minerals. Formation of clays from feldspar. All right, that's a good start to minerals. I'll see you soon for the next one.